All right, Year 12. This is just some final reflections about things that I think we haven't gone over in enough detail, and just on final reflections for me, looking through a couple of old IB exams and so forth that might occur. The first thing that I'm a little bit concerned about is we haven't really done much pendulum work in the QCAA syllabus. I think the reason for pendulums, swing side to side, okay? And so they actually form circular motion, but it's non-uniform circular motion. And so the QCAA only really focuses on uniform circular motion. But we're going to look at how there's a couple of different tricks that you can use with that circular motion here, as well as with a pendulum. Now, the first thing, if you have any sort of velocity questions with a pendulum, you have to think change in gravitational potential energy is going to equal to the change in kinetic energy. And I'm going to explain that now, okay? So as that ball is raised up to its maximum position here, it changes through a height. There's a change in height, okay? And we know that the change in gravitational potential energy is mg change in height, and that's going to equal 1/2 mv squared, okay? So at its maximum position, we know that the velocity is equal to 0, all right, which means the kinetic energy is equal to 0. Now, if that's the case, at the fastest position down here, we can say, well, there's been this change in gravitational potential energy, and that's equal to that velocity. Now, just like a couple of the other things we've done, because this is not traveling in a straight line, we can't use the Suvat equations, and so we get the m's cancelling out, multiplied both sides by 2, and then take the square root of both sides, and you get the velocity is equal to the square root of 2g change in h. Now, that's actually the maximum velocity, okay? So that's an important concept to know. If you get given anything on a rope that's swinging, don't try and work it out in terms of Suvat equations. Work it out in terms of change in height, changing potential energy. The next thing is I just want to have a quick look. It's very similar to breaking down the forces on an inclined plane. So we know that we have a mass here, okay, and that force down is equal to mg. Now, there's a couple of different ways we can put theta. Sometimes theta is here to the vertical, okay, sometimes the angle's there to the horizontal. Most of the time it's to the vertical, okay? So I can kind of see a couple of different questions here about, exam questions and especially experiments, and I'll talk about them in a little bit. Now, what we have, the force diagram, is we have this tension force, okay? So we have a tension force, and that's equal to mg. Now, if we balance this out, all right, if we balance this out, we can say, well, if that's theta up here, that this is also theta just from corresponding angles. So the F rule, if you think back to year 9 geometry, and then we can make sure we have the components that are equal and opposite. So that would be mg cosine theta, and this would be mg sine theta. All right, and what we actually know is the resultant force, just like an inclined plane, these will be equal and opposite, and the resultant force, I'll highlight it in green, will be this one down here. That will be the resultant force. So if we have a pendulum again, I'll draw it in green, the resultant force is always mg sine theta, where theta is the angle to the vertical, all right? But it's very rare, I think it'll be very rare that we actually get a question where we have to break it into these components. I want to look at how we'd break it into different components that are actually through the mass. So I'm just going to draw a vertical line there. Here's our string, here's our ball there. And so what we know is, instead of breaking up the weight force into different components, let's break up this tension force into different components. So this here is tension, yeah? And that means that tension force can be broken up into a horizontal and a vertical one, okay? Now, if this is theta at the top here, that means that this would be theta here from the z rule, and so that must be 90 minus theta. Or you can put theta up in this corner here and make it corresponding. Now, so what does this leave us with? So this basically leaves us with, if this ball is swinging around in a horizontal circle, which I think that they might ask us here. So imagine that going in a horizontal circle. So the horizontal circle, what does that say? Horizontal circle. What does that mean? That means that mg is going to equal to tension cosine theta. So that this component here, which is T cosine theta, is going to be equal to mg, because if it's moving in a horizontal circle, it means that its vertical force is 0 because there's no acceleration up and down. Now, this is where I'm saying, okay, well, if that's the case, this here would be T sine theta, and that would be your force net, which is T sine theta, which is going to equal mv squared on r because it's moving in a circle. Now the next step here is we can use this top equation here, equation 1, all right, to get an expression for tension. All right, and so from this top equation here, we can get then that if I just divide both sides by cosine theta, all right, I get tension is equal to mg cosine theta. Now if I substitute that in for this tension, what I get is I get mg cosine theta times by sine theta is equal to mv squared on r. Now, just so I don't make this really messy, I'm going to try and make it smaller. There we go. Now that mg, the m's cancel out from both sides, and sine theta divided by cosine theta here, that becomes tan theta. So we get g tan theta is equal to v squared on r. Okay, so we get tan theta into here, which is really important if we're moving in a horizontal circle. So things can swing around, and I'm anticipating that that could be a possible exam question. Just looking, we haven't done much on pendulums, it's kind of unfamiliar, so they might throw that in there. So just understand, I guess the key points is a recap, is you break the tension force up into horizontal and vertical components, and if it's not moving up and down, then mg is going to be equal and opposite tension cosine theta. Get an expression for the tension, substitute it in, okay, and we can go from there. The other way you could do it, or basically if they're asking what is the tension force, get an expression for, or go through and solve. So if they give you some experimental results for velocities or periods, remember with the velocities, if something's traveling in a circle, you might have to substitute in 2 pi r on period squared on r, okay? You might have to substitute in there. So if they're giving you experimental data, they might measure the period and the radius, and you'll have to find out what theta is. Now the next thing that's linking theta is, because this is an actual string as well, this might have some sort of length, and if that has some sort of length, you can use that as well maybe to find if this is r, theta is going to equal inverse sine r on L. So you can link that back in that way as well if they give you some length of string. So that's really important in terms of trying to link everything together. So if they give you some length here, the link is the theta at the top, and that in this expression here, you'd have to balance that out. It's a bit of a nasty question, but I just don't want to I just don't want to leave any stone unturned. So you can go through and do some of these questions, or think about these questions and play with those questions. And if you get one in the exam, be ready for it. I think that's all I have to do with pendulum. So here's one that they might ask. This is a pretty common experiment. So you have 2 charged particles, or 2 charged balls, which usually have the same charge on them, QQ. And what they can do is they measure the distance between the distance there. We'll call it D. All right. And so what we have is an application of Coulomb's law, right? So F equals K, and in this case it'll be Q1, Q2, which is Q squared over D squared, right? So that's the force applied on each ball, or each charge ball, okay? And what they can do is they can increase that charge and measure the distance in between them. So what's happening here is the balls also have mass, okay? And because they're in equilibrium, they also have the tension. So here you have the force due to Coulomb's law. So let's call it Fe, the electric force. You have the gravitational force, mg down, and then you have the tension force coming up. And so once again, what you'll have to do is you'll have to break the tension force up into this angle, and you'll get that tension cosine theta is once again equal to mg, and that tension sine theta is going to be equal to your Coulomb's law there. And so what they can do, as I said, they can change the Q and measure the D. Obviously, if one goes up, the other has to go up, or and which means it'll change the angle. So some nice little applications of that there. And so just spend some time drawing that up. So what happens if we increase the charge? Obviously, you're going to have a greater force going out. That greater force going out will increase the tension force in the horizontal, but won't increase the tension force in the vertical. And so we'll get an increase in angle. Some interesting thoughts around this whole idea of breaking this tension force up into vertical and horizontal components rather than breaking up the weight force into equal and opposite components to the tension. So what we do now is I want to look at one last thing, which I don't think I've gone over enough, just looking back over some of our past Flinders exams. And Mr. Strawn, who was here before us, was a pretty good physics teacher, and I was looking at a couple of his questions, which are not uncommon. But what happens if we had mass 1, mass 2, and we knew the distance between them, okay? But so say that mass 1 was greater than mass 2. All right, what that means is that the gravitational field will look like this. Okay, always coming towards, but there will be a place where there's an equilibrium position, and that equilibrium position is when the forces due to both of the masses are equal and opposite. Now this also happens with charged particles, and I just want to make sure here, if we're given this distance there, and they want you to find the distance from M1, you can call this X, okay? That this one here will be distance minus X, and they usually give you this. Now what we'll get is we'll get a situation where the forces are equal and opposite. So the force due to gravity on the M1 is just Newton's gravitational law, so it'll be G M1 on R squared. That's the gravitational field strength, I should say, not the gravitational force, because we're looking at the field strength at this particular point. And that's going to be equal and opposite G M2 on R squared. But we say R1 and R2. But what is R1 and R2? In this case here, G M1 on, we're going to say the distance X here, and we get G M2 on this distance, which is D minus X, and that's squared. And just to remind you, I know you're in senior, but D minus X squared does not equal to D squared minus X squared. Okay, it equals to D squared minus 2DX minus X squared. Okay, now cancel out the G's and you get this expression. Now there's two ways you can do this, and we're looking at the different techniques, and whichever one you feel comfortable with, you choose that one. Oops, I'm just trying to shrink this down a little bit. It's not happening. There it is. There it is. Bring that down there. Okay. So from this position, what they'll do is they'll probably give you M, and they'll give you D, and they'll ask you to find X. In your calculator, you can graph both of these. All right, and we just want this, where we have X down the bottom. and we have our y. So we'd put y1 equals here and y2 equals there. And on the same graph, what we'd do is, what's this going to look like? It's inversely squared, right? So one will look like that, and the other will look like that. And you can ask to find the intersection point. My tip here is that the window will be weird. So you'd make the base 0 to d, okay? Yeah, and then your y value, just type in the maximum. If you insert d into there and get a value for m1 over d, that will be m1 over d. That'll be your maximum window value, all right? And then you can ask your calculator to find that intersection point. It's hard changing the window in your calculator. The other one is you actually use the solve function in your calculator, and once again you've got to set a certain domain. You set it over the 0 to d domain, so whatever that distance is, and that will do that. So solve on calc, and the last one that you could do is actually go through and solve that theoretical, but I really don't want you to do that because it's so time consuming and there's lots of room for error. Now to solve that theoretically, if we bring this down here, we'd multiply both sides by x, and a d minus x squared up here, sorry, not x squared there, x squared there, is going to equal m2x. We'd expand that one out. No, we can't do that, I'm being silly. We go through and expand this out and multiplying it by m1 d squared minus 2dx minus x squared equals m2x. Now we expand it out, we get m1d, which is just a number, minus 2d m1x minus m1x squared equals m2x squared. I've lost a squared along the way, so I need to make sure I put that x squared back in. And it was a bit of a bummer that I missed that, but that's okay. So what we get now is we can then take the this away from this side, and you get something random like minus m2 minus m1 x squared, yeah, plus, yeah, I'll make it take 2d m1x, this is so much harder when there's no numbers in it, plus m1d, and that's going to be equal to 0. So let's talk about, you're given this, the mass one and the distance. You're given the d and this, so this is just a number, and then these two are just numbers, and so you end up kind of like ax squared plus bx plus c, which is the quadratic form, and therefore you can use the quadratic formula as you would remember. Okay, so lots of different techniques put involved into this equilibrium position. The original setup is the really important part. If they give you d, this is d minus x, this is x. Don't try and do this. I would try and solve on your calculator using the solve function, or do the intersection points. Okay. They're the tips I have that I've just been thinking that I didn't go over enough. Hopefully you found that useful. Best of luck, and make sure you come and see me in the next 2 days to prepare for the exam. Bye.